Hi everyone, so we are going to dive right into Chapter 6 now. Chapter 6 is all about looking at position, velocity, and acceleration functions. So some of it might look similar to some stuff you've done in physics, but we're going to look at the calculus aspect of it now. So first things first, let's talk about the position function. So the position function of an object moving along a line, say the x-axis, sometimes we'll say the x-axis, other times we'll say the y. Most of the time I feel like it's the x-axis. But regardless, it describes the location of an object at any given time. All right, position function we always call s of t. So let's look at example 1. A dynamite blast propels a heavy rock straight up with a launch velocity of 160 feet per second, reaches a height of this function, this position function s, after t seconds. How high does the rock go? Well, anytime it asks for how high, we know that we're going to be looking for a maximum. And we also know from the last chapter that if we're looking for the maximum of a function, we have to take the derivative. So we're going to find s prime and set it equal to 0 and then solve for x. Because that'll give me the time that we get the maximum, and then we can substitute it in to actually find the maximum height. So let's find s prime. So s prime of t is going to equal 160 minus 32t, and we're going to set that equal to 0. So we get 32t is equal to 160, so t is equal to 5. So that is the point in time in which I get my maximum, but I need to actually find the maximum value now, which means I want to find s of 5. So that means I'm going to do 160 times 5 minus 16 times 5 squared. So s of 5 is going to equal 400, and I need units, so feet. That means that the maximum height this rock goes is 400 feet. Okay, so we also have to talk about displacement. So the displacement of an object describes how far away an object is from where it started. So position tells me where it is. Displacement tells me how far away it is from where it originally started. So if we're looking at this interval from, say, time t equals 0, so from the start, to time t equals 1, whatever that happens to be, then my displacement is just going to be my end position minus my start position. So let's look at what this looks like. So we have this same function here, the same scenario, and it says at 4 seconds, how far away is the rock from where it started? So this how far away from where it started is the key that we're looking at the displacement. Which means I need to look at s of 4, because that's where it's ending, right? It's at 4 seconds. Well, and it started at time t equals 0. So I want to do s of 4 minus s of 0. So all that means is take 4 and plug it into my function here. So I've already done it ahead of time, so I don't have to plug it into my calculator. But if I plug 4 into this function, I get 384. And if I plug 0 in, I obviously get 0. So I get that my displacement is 384, and again I need my units, so feet. And that's all that is. Check my math, right? Use your calculator, double check and make sure that I did that one right and that I did that one right, but I think I did. It's always good for you guys to check just in case. Okay, moving along here, now let's talk about average velocity. Well, we've talked about average velocity a lot. You guys should be pretty familiar with that already. Average velocity of an object over a given time interval describes the average rate of change. So we didn't call it average velocity before, we just called it average rate of change, which we know is just regular old slope. Velocity can be positive or negative because it describes how fast an object is moving and the direction it is traveling. So if we're looking at that same time interval from t0 to t1, and I want to find the average velocity, the notation we're going to use here is just v average, and it's just going to be the slope. So it's going to be the position at t1 minus the position at t0 all over t1 minus t0. So again, regular old slope, and hopefully when you look at this you can notice that the top there is actually that displacement that we were just talking about. So the average velocity is really just the displacement over the change in time. So same function, same scenario here, but now it's asking what is the rock's average velocity over the time interval from 0 to 3. So we know that the average velocity is going to be equal to s of 3 minus s of 0 all over 3 minus 0. So again, average rate of change just means regular old slope. So if we plug in s of 3, then we get 336. S of 0 we know is 0. 3 minus 0 is 3. So we have 336 over 3. That means the average velocity is 112. And again, we need units. Velocity is measured in feet per second in this example. So the average velocity is 112 feet per second. So average velocity, now we're going to talk about instantaneous velocity. Well, this word instantaneous should pop out at you. We know that instantaneous anything means that we're taking a derivative. So the instantaneous velocity is the derivative of the position function, and it describes how fast an object is moving at a moment in time. So velocity we call v of t, and it is the derivative of the position function. It's the first derivative. Alright, so question 4 gives us this same scenario, but now it says, what is the velocity of the rock when it is 256 feet above the ground on the way up? So we have to take a step back and kind of think about this for a second. We want the velocity when the rock is at 256 feet above the ground on the way up. Well, if we launch a rock, we know that it's going to go something like this, right? And if we say 256 feet is right here, then our rock is going to go up, it's going to surpass that 256 most likely, and then it's going to have to come back down and hit the ground. So we're looking for where it crosses 256 that first time. We're looking for that value right there. So we need to find that time value. So in order to do that, we need to know when the position is equal to 256 feet. So we're going to start with that. 256 is equal to 160t minus 16t squared. And we're going to find the point in time, or both points in time, where the position is 256 feet. So I'm actually going to move both of these over to the other side so that I can have a positive 16t squared, and then a negative 160t plus 256, and it's going to equal 0. So if we factor out a 16, we'll have t squared minus 10t plus 16 equals 0. And we can factor that, which means t minus 2 times t minus 8, because we want to multiply to 16 and add to negative 10. So we get that t is equal to 2 and that t is equal to 8. So we know then we're looking for when it's 256 on the way up, that's clearly got to be at time t equals 2. So really this question is asking what is the velocity at t equals 2. So in order to find that, we need to actually take the derivative of the position function. So v of t, which is the same as s prime of t, is going to equal 160 minus 32t. So if I want to find v of 2, I'm just going to substitute that in. So 160 minus 32 times 2, we get that the velocity at 2 is equal to 96, and it's velocity, so we're talking about feet per second. And we do need to have units on that. Again, double check my math and make sure I plugged that in correctly, but it should be 96 feet per second. Okay. I know I'm moving a little bit fast, but there's a lot of information in here, and I don't want you guys to have a super long video. So, hopefully you guys are cool. Pause if you need to write down what I'm doing or calculate or whatever. So now we're going to talk about the particles or objects moving right or moving left. So when we're trying to decide the direction of an object or the direction that the object is traveling, we look at the sign of the velocity function. All right, well, velocity we know is v of t, which is really the first derivative of the position function. So this should seem fairly familiar. Moving to the right and moving to the left is kind of like looking at where a function is increasing and decreasing. And we know that in order to do that, we need to look at the sign of the first derivative. All right, so this is all connecting back to chapter 5. So same situation here, but now we're looking at when is the object moving to the right and when is the object moving to the left. Well, in order to figure out, or in order to know, if the object is moving to the right, that means we need the velocity to be greater than or equal to 0. And for it to be moving to the left, we need the velocity to be less than or equal to 0. So in order to figure this out, we're going to have to actually find the velocity function. So we've done it already, but we're going to do it again. V of t, which is the same as s prime of t, is equal to 160 minus 32t. And if we set that equal to 0, 160 minus 32t, we've solved it already, so I'm just going to go ahead and jump right to t equals 5. So we know that that's a critical value. All right. Now, similar to what we did in the last chapter, we're going to make a table for the first derivative. It's just that now our first derivative, instead of writing s prime of t, we're just going to call it v of t, because that's the velocity function. Now, something that's a little different, because we're talking about t being time, we don't want our end value here to be negative infinity. We want it to start at 0, because it's dealing with time. So then we've got a 5 here, and then we go off to infinity. So if we want to do 2 equals, let's say 1, if we plug a 1 into this velocity function, we know that it's going to be positive. And then let's go ahead and say, let's plug in t equals 6. If I plug that into my velocity function, I know that it's going to be a negative. So now looking at this, I can figure out when the object is moving to the right or to the left, because if velocity is positive, it's moving to the right. So I can say then the object is moving to the right on the interval from 0 to 5 because the velocity, v of t, is greater than 0. And remember, this is a closed interval because we're talking about increasing and decreasing. I can also say then that the object is moving left on the interval from 5 to infinity because the velocity, v of t, is less than 0. It's negative. So those are our justifications there. It's the same as when we did justifications in the last chapter with looking at when a function is increasing and decreasing. We're saying that the Object is moving to the right when it's positive, and it's moving to the left when the velocity is negative. So similar to velocity, now we have to talk about speed. So the speed of an object is the absolute value of the velocity. For speed, we're only looking at how fast an object is moving. We ignore the direction. So velocity can be positive or negative because we look at the direction, whereas speed, we take the absolute value because we just care about how fast it's moving. So speed is equal to the absolute value of the velocity function. So same scenario, and we're looking at what is the speed of the rock at time t equals 2 seconds, which means I'm really looking for the absolute value of the velocity at t equals 2. So my velocity function, we already know, is 160 minus 32t. So if I want to do the velocity at 2, it's 160 minus 32 times 2. So the velocity at time t equals 2 is 96 feet per second. And since that's already positive, the absolute value is still going to be positive, so this one we didn't really have to worry too much about it. However, if it was negative, we would have to take the absolute value there. I know this is long, bear with me, we're almost done, okay? I have one more thing, well, two more things to talk about, mainly just some vocabulary. Alright, so acceleration. The acceleration of an object describes how fast the speed of the object is changing. Therefore, it is the derivative of the velocity with respect to time. So acceleration we call a of t, and it's really equal to v prime of t. Now you have to remember, velocity is the derivative of position, which really means we could also say that acceleration is the second derivative of the position function. So let's take a look here. Same scenario. Now we're looking at the acceleration of the rock at time t equals 2 seconds. Well, velocity, which is the first derivative, is 160 minus 32t. And then if I want acceleration, that's the derivative of the velocity, which is just negative 32. So this is constant then, regardless of the time. I know that my acceleration is negative 32, but let's go ahead and specify we want the acceleration at time t equals 2, and it's negative 32. Acceleration is always in feet per second squared. When we talk about a function speeding up or slowing down, we can also say that the speed is increasing or speed is decreasing. But in order to do that, we look at both the velocity and acceleration functions. So if the velocity and the acceleration have the same sign, so either both positive or both negative, then the object is speeding up. So regardless of if they're both positive or both negative, as long as they're the same, the object is speeding up. If the velocity and acceleration have opposite signs, if it's one of each, then the object is slowing down. So, same function, same scenario. We're looking for is the particle speeding up or slowing down at time t equals 2 seconds. Well, if I'm looking for is it speeding up or is it slowing down, we need to compare the signs of the velocity, so v of 2, and the acceleration, a of 2, because then I'll be able to figure it out. Well, we already found earlier that v of t is 160 minus 32t. We also already found that v of 2 is equal to 96 feet per second. And we found that the acceleration function is negative 32 regardless, and so a of 2 is negative 32 feet per second squared. And when we look, the velocity at 2 is a positive 96, the acceleration at 2 is a negative 32, so we can say then that the particle is slowing down at time t equals 2 seconds because the velocity at 2 is greater than 0 and the acceleration at 2 is less than 0. So since those are different signs, we know that the particle is slowing down. All right, I know that that was a little bit longer. We are going to do tons of practice though so that you guys can get really, really good at this. This shows up a lot on the AP exam, so we need to make sure that we understand this. So if you've got questions, please, please, please ask them.